once it starts recording, minimize that. We are recording. Hello everyone, how is it going? I want some reply just to make sure that I am connected with you, please.
Yes, we can hear you, Doctor.
So, yesterday we started with the phase diagrams and we dealt with basically with the binary isomorphous phase diagram, and we said what is binary isomorphous phase diagram. For example, was the copper nickel system, the binary isomorphous. Binary means a system with two components, that's binary. And we also said isomorphous. You notice that the most appreciable feature, the most noticeable feature of this phase diagram is the unlimited solubility of the copper and nickel, or nickel and copper there, as you can see in all the solid solution for all the for all the values of the compositions there. Between the nickel and copper, you only have one phase, one crystal structure type, which is the FCC, which is the solid solution, the alpha solid solution there. It does not produce anything else. And the name is coming basically isomorphous from there. Iso means one, and morphous comes from the morphology, which is the crystal structure. So you have one crystal structure there. So this is why we called it like that. And we also practiced how we can use the phase diagram in order to answer those questions, like how many phases do you have if you are given the temperature and composition, how many phases do you have, what these phases are, what is the composition of the phases that you're having, and what are the proportions of the phases that you're having there. So we answered these questions, having practiced that with having the temperature and composition for the binary isomorphous phase diagram. Today we are going to look at C, because that's also important, the development of the microstructure in isomorphous alloys. So what are we going to do? We are going to look at how the microstructure of the material is going to develop if we cool down slowly using the phase diagram. So for equilibrium cooling, and what is the equilibrium cooling? We said last time. What is it? What do I mean by equilibrium cooling when I say equilibrium cooling? I need answers. Last time I explained
slowly.
meaning. Yes. Last
So
time yes.
the
Go
phase
ahead.
arrange in a certain way.
You said a word there. You're missing again here. You said the cooling is slow, right?
Yes, to
This is
arrange the phases in the less
Yeah, if you remember, we
energy.
explained here the first, not here, here we explained phase equilibrium. It's dictated in the phase diagram. The conditions are dictated by phase equilibria, which means what? Which means that we cool very slowly because the diffusion in the solids is very slow. So you need to leave enough time for the transformation to happen. And the phase diagram is based on that. It can predict for you the phases which you will be developing, provided you give it enough time for the transformation to complete, and give you the stable configuration. So in the phase diagram, the stable configurations are given there because you allowed it enough time or sufficient time for the transformation to happen. And this is the diagram. So when we say equilibrium cooling, which means that cooling occurs very slowly, in order for the phase diagram to predict for us, to give us the information on the phases which are going to develop. phase equilibrium is continuously maintained. That means also that you are not jumping in temperature, although you are cooling slowly, but you have a big jump. No, that is not the case as well. So you are maintaining continuously that condition. We are going to consider the copper nickel system, which is the binary isomorphous behavior, complete solubility of one into the other one. We are going to consider cooling of the alloy at 35% by weight nickel, which has 65% by weight copper, and we will be cooling from 1300 degrees centigrade and moving down on a vertical line and see what will be the development of the microphone. Do that here. So we will start from that's part of the phase of the copper nickel phase diagram. That's part of it. This part is not shown here. That part as well. We are concerned because in the picture here. So we will start at point. Let me use the other cursor. Maybe it is more clear. I noticed when I review the recordings. So we will start from point A. At point A, which is at 1300 degrees centigrade, and we are at 35% by weight nickel. That's the composition of the alloy. So if we have these two conditions on the phase diagram, I can determine my coordinate. My coordinate will be at point A. At point A, how many phases do we have? We have one phase only, a single phase. We are in the single phase area. What is the composition of that phase? It is the composition of that phase is the composition of the alloy. What is the proportion, the weight fraction of that phase? It's 100% liquid, as we say. So those are the four questions which we answered now. Now, if you, as we said, adhere to the or stick to the condition of the phase diagram, which is very slow cooling slower than the diffusion process, which will happen in the transformation of the phase of the atoms there, or movement of the atoms. If you cool down, nothing is going to happen. Nothing is going to happen until you hit the liquidus line. This is called the liquidus line because above which everything is basically liquid. So once you go just below that line, something else is going to happen, because in this region here you have liquid plus alpha solid solution. So the alpha solid solution will start to nucleate. يعني يتكون. So once you hit below that line, you can see you have another phase developing, and these phases are going to nucleate in the liquid at different spots. Of course, which spots will start that? It will be the coolest spot in the material, because as we have already mentioned there in chapter 3 and 4, both of them, we said that the temperature is not homogeneous across the material. Was the temperature homogeneous? No, it's not homogeneous, and that's why the coolest spot will start to develop or nucleate a grain, a solid grain, and then the next one, and then the next coolest, and then the next coolest in different areas, basically in the material. And these crystals which nucleate, they develop the crystal, the atom's orientation will be different in each one of them. So that will start nucleating, and once it starts nucleating, as we go down with the temperature, it's going to grow as well. As you could see, as we go further down, they are going to grow in size in random orientations of the atoms. So as we said, and as we go further down, more these are going to grow bigger and bigger and bigger, and more nucleation could happen there as well at the same time. But let us pay attention to this. Now, as we go below that line, we have two phases, the alpha solution and the green, which is the liquid. Now, from at that point, what is the composition of the solid and what is the composition of the liquid? We just draw the tie line there. We will see that the composition this is the solidus line, so this gives the composition of the solid, so it's 46, and the composition of the liquid, when we strike with the liquidus line, we get the composition of the liquid, so it is 35% by weight nickel. And of course, from the tie line there as well, from Liver's rule, you understand the amount, the proportion of the liquid will be related to, or the ratio between the far segment of the tie line, which is this, divided by the total length of the tie line. As you can see, this is a big line, a big segment of the line divided by the total will give you majority of the phase is liquid. While the solid, it's this segment actually, it's the far, this is the solidus line, this is the solid, it is the far segment of the tie line divided by the total one. So you have a small segment there, so it's a small amount, as you could see, of the alpha solid solution there. But as you go down, there is a change which is happening. The compositions are changing. So this is the composition of the solid, and that's the composition of the liquid. As you go down, the composition of that solid and the liquid is not constant. It is variable. It's changing. As we go down further, at this point, at point C, for example, the composition of the solid becomes 43%, and the composition of the liquid becomes 32% by weight nickel. And from here at point C, you can notice that the amount of the liquid reduced and the amount of the solid increased. How much is the amount of the solid ratio? Let's say percentage. It's this of the solid. It's the far segment. It's this divided by the total length there, and the proportion of the liquid will be this divided by all that. As you could see, that segment reduced in size and this segment increased in size. So you are having an increased amount of the solid happening in the material. And at this spot, just below the liquidus line, the first solid is going to develop. The nucleation of the solid is going to develop at just below that line. And as we go further and further down, just before we hit the solidus line, that will be the last remaining liquid in the material, and the last remaining liquid in the material has a composition. If we draw the tie line, has a composition of this much, which is 24. Of course, that 24 is read from there. Yani all the readings are taken from here, 24%. All the readings there which we are mentioning. You just drop a vertical like this and do the reading there. So that's the last spot, the last liquid in the material has 24% by weight nickel, and it has 36% by weight. The solid has 36% by weight nickel. And once you go below the solidus line, now everything turns into the solid. So as you can see, it becomes bigger and bigger and bigger, and as we know, they are going to impinge against each other with the mismatch of the orientations of the atoms there. But once they impinge, then they make the grain boundaries, as you can see, and develop a polycrystalline material as we have. But the composition of that polycrystalline material will be the composition of the alloy, as you can see there. So this is how the development of the microstructure in the binary isomorphous phase diagram system, let's say, happens. Why we do that? Because, well, actually we need always to know the history of the development of in this case or in the different cases, how the structure of the material or the microstructure of the material develops, because we cannot just go to a point and say, oh, ting this point and let us see what will the microstructure be. As I told you at the beginning of this chapter, we need the tool, which is the phase diagram, which helps us to predict what phases we are going to get. But in addition to that, we need to know the history of heat treatment, how it was treated. So this is very important to understand in developing in predicting what microstructure of materials we will be developing, or when it comes to designing the microstructure, how we will be able to design the different microstructures to get different properties of materials. In terms of mechanical properties of the copper-nickel system, that is also important, because why are we studying the microstructure development? Well, basically to be able to predict it or to be able to design the microstructure. So why are we trying to predict the microstructure or design the microstructure? Because we want to get required, let's say, mechanical properties of the material, and this is what we want to do. So because the mechanical properties are correlated to the microstructure of the material strongly, this is how we do it. This is how we proceed with designing the mechanical properties of the material. In the copper-nickel system, the solid solution itself, when we make a solid solution, it causes the strengthening actually, and this is the strengthening in the material. It's called solid solution strengthening. There are different strategies that we could use in order to cause the strengthening of the material. In this case, it's an increase in the strength and hardness of an alloy by the addition of another component, another atom to the material, basically other atoms, other alloying elements means that. So this causes what we refer to as solid. It develops a solid solution, and that solid solution is the strengthening, and using that is called the solid solution strengthening. Now you can notice that with the addition of the nickel, what is happening? So this relationship shows the tensile strength there in megapascals with the versus the addition of the nickel, the composition there, the change in the composition. As we go in this direction, more nickel is added, composition of nickel and weight percentage. You can notice this. What happens when we are adding more nickel to the copper? The copper starts here, the tensile strength for the pure copper, and as we add nickel, the tensile strength of the material is increasing to a maximum reaching at nearly 60% by weight nickel. And then beyond that, you will have a decrease in the tensile strength to reach actually the tensile strength of the pure nickel when you have 100% by weight nickel. Notice this is very important. The strength of the material, the tensile strength of the material that we are getting there is much higher than the tensile strength for the pure copper and the tensile strength for the pure nickel. This is where we are saying when you add an alloy, you are causing strengthening effect. This strengthening which happens to the material is more than the strength of the pure nickel and the pure copper as well. So that is the astonishing part of the strengthening behavior of the material. At the same time, you can see something else. We can study also the elongation. That is we can say percent elongation, the ductility of the material, basically, which we have a measure to do that, which is the percent elongation versus the composition again. In this case, we said we are increasing the strength with addition of nickel. As you can see, we are reducing. That is the ductility, percent elongation of the pure copper. We now notice that the percent elongation reduces actually as we increase the nickel composition, the amount of nickel in the material, to a minimum actually at nearly the same amount where we have the maximum tensile strength there. There we have the maximum tensile strength there, which is happening at 60%. The 60% causes the material to be at its lowest level of ductility. So as we could see, and increasing more, it will go back to the pure nickel behavior. As you could see from here, that the rule of thumb here is shown very clearly in the solid solution strengthening there. Increasing the strength, as you could see there, reduces the ductility, and increases the ductility, reduces the strength of the material, or the other way around. Increasing strength increases ductility. Reducing strength increases ductility. So that is the rule of thumb that we have talked about long back, right from the beginning of studying this material. Normally, people, in order to design materials, take the figures like that and overlap them really in order to get, of course, I did not prepare that very well, yeah, like this. So from here, you can see what your choices are in selecting the optimum composition of the material. For example, some people choose that as an optimum value between the composition, between the ductility and the strength of the material. You have good strength and you have good ductility as well. But if you want them more ductility, so you go for higher strength, but that you understand that how much ductility you're using there. So this is also a way in order to get the optimum behavior of the material when it comes to both, when you consider both ductility and the strength of the material.
دكتور
Yes.
لما حطيت الكيرف مال الدكتيليتي على اللي هو مال التنسايل سترينث كان في نوع اللي هو باوندري يعني كلوزد باوندري. هل الاريا في الكلوزد باوندري does it represent something يعني؟
No. We are looking at optimum properties يعني between these two. You could have these are statistics methods actually to choose optimum properties. صح? You were putting there in order to see where they are going to intersect, at what value exactly you are having that intersection there. So normally people say, okay, this is a good intersection point where you have high strength and high ductility at the same time. But in some clients' requirement for material, for example, they would want more strength. As you can see, the curve was going like that. You would want more strength to get there, but you would know how much ductility you will be losing from there. But the curve between or not between, that is not that is not an issue for us here. Okay. So that is to show how this is happening and what's the relationship between the composition which we are showing here, which is alloying, which is the addition of the nickel, to the ductility and the strength of the material. Now, we finished from the binary isomorphous phase diagram. We want to start with the second type of the phase diagrams, which we refer to as the binary eutectic. And then binary, it's the same name that we have dealt with. It's a system with two components that we already mentioned there. And the other name is, we dealt with binary isomorphous previously. Now we will be dealing with binary eutectic. So what's the meaning of eutectic? Basically, eutectic means easily melted, which has a special composition with a minimum melting point temperature. We will come to this point in a minute, but let us first of all look at an example of the phase diagram, and we introduce it to you, and we introduce ourselves to it, and then we will talk about what eutectic exactly means now. We will deal with the copper silver system, binary, it's two components. As you could see, this is the phase diagram. It looks completely different from the binary isomorphous phase diagram. To start with, of course, this is the temperature in degrees centigrade, and that's the composition. It's given here in terms of weight percentage of the silver, as you have. We notice in this, it's a little bit more involved, the phase diagram. You have single phase regions here. This is a single phase region, which is liquid. All that region is a single phase region, which is liquid. This is a single phase region. It is alpha solid solution. And that is a single phase region also, which is beta solid solution. We have also two phase regions, not one, three phase regions basically. So you have two phases occurring there, liquid and alpha solid solution. In this triangle, we have the liquid and beta solid solution happening together. And in this area below that line, basically, we have the alpha plus beta, both of them solid solutions basically happening there. The alpha solid solution is mostly copper. So if you look at if you look at the weight percentage, the composition, we are in these ranges basically. So most of the alpha is copper. On the other hand, beta is mostly silver, because we are in this range basically. The amount of silver is the overwhelming majority of the atoms there. So we can say that alpha is basically the alpha solid solution is a solid solution where we have the solute is the silver and the solvent is the copper. And the beta solid solution, basically, it's a solid solution with the mother material being the silver, and the solute that you are adding there is the copper. So you could say that in this way. That line there is the liquidus line. As you could see, beyond that line, everything is liquid. And this line is called the solidus line. Coming from there to here, everything turns into the solid. The same thing for that line as well. It's called the solidus line. This line here is called the solvus line. It's I don't want you to figure out where it is written. So this is called the solvus line. Going from solid to two solids, or from solid to two solids, is the same thing. So this is alpha. You could be passing that point. You will go from one solid to two solids basically, because here we have two solid solutions, the alpha solid solution and the beta solid solution. From here as well, if you go from here to there, going from beta solid solution into the alpha solid solution and beta solid solution, that's why these two lines are called the solvus lines. Now, what is happening here? As if we are, for example, to determine the melting point temperature of pure copper, let's say, how do we determine the melting point temperature of pure copper? From what we did from the last phase diagram. If I ask you what is the melting point temperature of pure copper, what will your answer be?
It will be on the graph, on the
Yeah, I know on the graph.
liquid line.
دكتور 1100.
Yes.
Yes. So you go to 0% by weight silver, which will be 100% copper, صح? From there, you know, if you raise the temperature, you're in the solid. Here it's solid. Here it is solid. Where is it going to melt? Just above that line, which is nearly 1100 degrees centigrade, isn't it? So his answer was correct. So once you go beyond that line, it directly melts from the solid solution into the liquid, which is called the direct melting. If you remember, we did that also for the, here we said the melting point temperature, it happens directly there. For pure materials, it happens directly, going from a solid here to a liquid here. That's a liquid heating. All this range is liquid. So across a point, the melting which occurs for pure materials happens directly. It's called direct melting. It's called simple melting. Or simple solidification, if you want, if you're coming back, if you're cooling, for example. So this happens for pure metals across a point. The same thing here. The nickel, pure nickel, the melting happens across a point. While for an alloy with different compositions here, it does not happen across a point. It happens across a range of temperature, as we have explained last time. So this is the norm actually, which happens. This is the rule. This is the behavior of pure metals and non-pure metals basically. Diagram which we are talking about, there is a big exception which we have here. Now, for pure metals, the melting happens across a point here, that is pure copper. For pure silver, what is the melting point of pure copper? Again, you go up there, it is solid, solid, solid. Just across that point, you will go from the totally solid solution, a beta solid solution, into the liquid directly. So it happens. So for pure silver, also happens across a point. But when you have an alloy, when you have a composition of the different things together, like the copper and the silver in this case, when you want to melt, as you are increasing the temperature, no, it happens across a range of temperatures. As you could see there, صح? It goes first into the from the solid into the liquid and solid and changes until you reach that temperature. It goes to the liquid, except for one point, which is this point, and that is called the eutectic point. Eutectic means simply melting. This is an exception point in this phase diagram where this behavior, actually due to this point, the phase diagram is called eutectic. When you have a guy with long nose, you call يعني في فريجنا مثلا كان في واحد عبود اسمه عبود كان طويل وايد فكنا مسمينه عبود طويل لأن كان عندنا عبد الله وايد نسميه عبود طويل. So this is the distinguishing part in this phase diagram where the name is called after. هذا الشيء المميز في هذا الفيز diagram اللي الاسم ينقال وراه، نفس عبود طويل أو شو يسمونه أنوار أبو خشم معود مثلا. أنا ما قاعد أحاول أتفنن just to make it clear for you what I mean. In the previous one, the most distinguishing in the binary isomorphous phase diagram, the most distinguishing character of that phase diagram is the complete solubility, and that's why it's called isomorphous. So this is the most distinguishing thing about that phase diagram, this phase diagram, and this point where this happens is called the eutectic point. And the temperature at which this happens is called the eutectic isotherm. So that line which is drawn there, it's called the eutectic isotherm. Iso يعني شنو? Iso again, it's one. Therm يعني from thermal يعني temperature basically. Isotherm, which means a constant temperature. This is what we are talking. And that eutectic point basically occurs at the composition of silver of about 71.9% by weight silver and at a temperature of 779 degrees centigrade. So this is why we call it eutectic. And what is that eutectic point? Is this point. Where does it happen? It happens at this temperature and this composition. Notice solubility lines here as well. You can see that in the alpha solid solution, in this case, not in the previous, not in the binary isomorphous, it has limited solubility. There we had unlimited solubility, complete solubility of the copper and the nickel, or the nickel and the copper. Here we have limited solubility. The limited solubility here, you have the points which we have. Okay, the next phase diagram gives us letters. It's better to look at this, this is the limit. It goes from C, B, A. It gives the line, actually that line gives the solubility limit of the silver in the copper basically, or in the alpha solid solution. And again, here as well, H, G, F, that line there gives the solubility limit for the silver, for the copper in the silver as a mother material, because in these portions or in these compositions, the mother material in the beta phase is basically, you know, it is basically the silver. The biggest amount, or let's call it the solvent, actually المذيب يعني, the solvent is the silver, and the solute will be in the beta solid solution will be the copper. So that represents the solubility. as we increase the amount to start from this part, from 0 copper, as we increase the silver in the copper as a solid solution, we notice that that's the melting point temperature of the copper. What does it do basically? Adding the silver, it is reducing the solubility. It is reducing the melting point temperature further and further and further and further until it reaches to the minimum melting point temperature at the eutectic point, and then increasing the amount of silver, as you could see, further increases the melting point temperature to reach to the melting point temperature of the pure silver, as you can see that. And there is actually practical application to that point when we add one to the other. Once it's reducing the melting point temperature, there are applications like making thermocouples. We will see that in a minute. How does that work? So basically, to revise what I already said, the alpha phase is a solid solution rich in copper. That's the alpha phase. Silver is the solute component, and copper is the solvent basically. Only a limited concentration of silver can dissolve in the copper, and that is dictated by the solubility line which I have mentioned here. The beta phase, it's a solid solution rich in silver. That's the beta phase. It's rich in silver. The solvent is basically silver, and the solute is the copper. Copper is the solute component. Both the alpha and beta, Now, if you want to look at the crystal structure type, since we are talking about the copper and silver, what is the crystal structure of the copper?
FCC.
FCC. What is the crystal structure of silver?
FCC also.
Both of them are FCC. So basically, if it is a solid solution, you cannot be saying you will be adding another material which has a BCC, for example, to it. So since both of them have the silver and the copper, both of them have the same FCC crystal structure, then the solid solution which form will be also an FCC crystal structure. So both alpha and beta are FCC crystal structure. Solubility limit, which we have already talked about, these are the solubility lines, and we said to a maximum which is at the eutectic point. And in the binary isomorphous phase diagram, we had unlimited solubility, and we said there are some reasons. We said there are reasons to make the solid solution or otherwise to form another phase. Though there were 4 conditions which we mentioned, which is the crystal structure type, the atomic size factor. Basically, we said the valency, and we said the electronegativity. Both of these last 2 ones reflect the energy of the atom basically. In the binary isomorphous phase diagram, we saw that the crystal structure type were the same, atomic size factor and the energy of the atoms there, valency or the electronegativity, were very close to each other, which causes the complete solubility one into the other one. In this case, although the crystal structures are the same for the copper and the silver, but their sizes are not actually quite close. They are different, and also their valencies and their electronegativities are different, and that's why it causes this limited solubility of one into the other one. And this is what I'm saying in the last paragraph here. As I already mentioned, this I already explained. We are just going to repeat it here. As silver is added to the copper, the liquidus temperature decreases, and this is what I have shown. As silver is added, the liquidus temperature decreases to a minimum melting point at the eutectic point. Now, and when you increase, then something else happens above that line. Now, this eutectic point is normally expressed by a chemical equation, which we can always show when here 10. cannot see anything. Where is my mouse? All right. Now, this point, which is the eutectic point, is normally expressed by a chemical equation there. So what we do is that we say what happens when we cool down in this direction. What happens? It goes from a liquid basically to two solid phases there, which are the alpha and beta. So this is represented basically by, by a chemical equation. We say we go from liquid basically just above the eutectic in order to explain what happens at the eutectic point, which we refer to as the eutectic transformation. So we say we start with the liquid basically, and that liquid is at, what is the composition of that liquid? It's basically, you can read it from here down here, you draw a vertical, you read it from there, or basically the information is given there. Liquid at 71.9%. By weight, (71.1) by weight, silver. We don't need to write the others as well. So this gives what? As we cool down from just above the point to just below the point, what happens to just below the point? And this happens at what temperature? It happens at 779 degree centigrade. I can write the equation beforehand and show it to you just like that, but I want to show you that I'm not memorizing this. How do we express the eutectic transformation? We express it in this way. I get the information all from the phase diagram. You just need to understand it. You don't need to memorize it. You're coming down from there. You have a single phase region, which is liquid, just above that eutectic point to just below that point, which gives you what? Two phases, alpha, which has a composition, plus beta, which has another composition. And from there, tie lines, we can get what the composition of alpha is. If you are going from here to just below that point, now just below that point, what will be the two phases? Will be alpha and beta. How do we get the compositions there? We draw a tie line. We draw a tie line, which we did last time. It is going to intersect that line here. This is the alpha, so you will be getting the composition of the alpha phase from here. So you will drop a line from there, but the value is given to you here as well. So you will have, and you intersect with the Sylvus line here to get the composition of the beta phase. So you can drop from here there down, but you already have been given the value there. So with alpha, and alpha has a composition of how much? 8% by weight. Silver. Okay, and the beta, which has 91.2. 91.2% by weight again silver. So you can see we have developed the equation where we can explain or we can show the eutectic transformation. Normally this equation is used in order to express the eutectic transformation which happens in the binary eutectic phase diagrams there. And this is
دكتور
yes.
في اللي قبل لك تكتبه في نسبة ناقصة إذا بتجمعهم بيبقى لك 0.8 عشان 100%. هذه impurities يعني.
وين النسبة اللي ناقصة بالضبط؟ قول لي إياها على أساس ما فهم.
الحين هو 8% و 91.2 إذا بتجمعهم بيصير 99.2.
No, this is you cannot don't. No, your understanding is not quite correct. You add these two will not be adding to 100. You mean adding these two values will add to 100? This is what you mean? No, this is 91.2% by weight silver. Okay, I'm not writing the rest because it will be very lengthy. Let me see if it is written here. In this one, no, again, it's not written, but in this one, it's 8% by weight silver. You can put a dash and say كم من المئة ناقص هني 92 صح؟ من المئة ناقص 92 صح؟ You say 92, yeah, 92% by weight هذاك silver بيكون هذه copper in each one of them. So you can do that. But since when I say silver is this much, I don't need to write that because this is binary. I don't need to write the rest, which is the silver, which is the copper, sorry. So this all together will be 100, yes, but not this with that one, of course. This is a solid solution and that is another solid solution. Here as well, not the same thing. So here in the case, we have 100 minus 91.2. This gives how much? It gives, and we have put a slash and 8.8% by weight, copper. So now this to that they add up to 100, and this to this they add up to 100. This is a different sort of solution, and this is a different sort of solution. In each one of them you have the balance, yes. بس ما له علاقة إن تقول you add these two together. لا. This is solid solution and this is the difference of the solution. You are looking at the composition of beta long and of the alpha long. Okay, واضح؟
دكتور؟
واضح دكتور.
تفضل.
يعني هني هاي الكومبوزيشن، بس إذا شفنا البروبورشنز الألفا والبيتا اثنيناتهم 100.
Yeah, we're not looking at proportion now. We are looking at the composition in this equation. Okay? We're looking at compositions only here. This is composition and that is composition. For the proportion, this will be different. We will see that. We will practice that. Maybe not today. Time is not really much here. But we will see how we will get the proportion as well using the Lever's rule in the same way we did in the previous system as well. So let me finish this part at least. So this is what we are. The two liquids meet at the point E, which is the eutectic point called the eutectic point, which is an invariant which happens at 779 degrees centigrade and at a composition as we have seen in this case. We have different systems there. In this case, it happens at 71.9 by weight nickel. Eutectic means easy melting, which we have already mentioned. The eutectic reaction takes place. This is the equation that I have already shown you. Upon cooling, this is going to happen. Liquid at 71.9% silver, and of course the rest will be copper. It gives you the alpha solution at 8% by weight silver and 92% by weight copper, and the beta phase, which is having 91.2% by weight silver, the rest will be copper at 779 degrees centigrade. If I ask you to write an equation or the eutectic equation, for example, this is what you are going to write. Eutectic equation is similar to the solidification and melting of a pure components. The melting or the solidification across the eutectic point, it happens in the same way it happens to the pure melting material. It occurs across a point, but for different compositions, they occur across a range of temperature. Eutectic, this is what we are saying, it happens across a point. Eutectic reaction is similar to solidification or melting of pure components. I wanted to show you also another example of the I think we don't have time today. So anyways, any questions now? This is just to introduce that, this is another system which I wanted to also you to see, because this is also used practically in industry. We will see this system next time. This is also a eutectic, a binary eutectic system, binary. So you have two components there, the lid and the tin, and it is eutectic because it behaves in the same way. This is the phase diagram. It's the same animal that we have seen in the previous system, same shape, but of course for a different system. You can see the eutectic point occurs at 61.9. The eutectic isotherm, it's 183 there. We had 779, nearly 800 degrees centigrade. So the shape of the phase diagram is the same, but the variables that you have there are quite different. We will leave this for next time. We are going to finish this next time. Hopefully we need 1 or 1.5 lecture to finish this chapter, and then we will start chapter 10. Any questions?
دكتور
Yes.
يعني شنو اليوتكتيك ايزوثيرم؟
Eutectic refers to the eutectic point, صح?
صح.
Now we notice in the phase diagram that there is a line at the eutectic point, which is this line. It is a constant temperature. So it's called eutectic temperature because eutectic temperature occurs at 183, which is the temp temperature. It's called eutectic temperature, and it's called eutectic isotherm because the iso يعني شنو؟ iso يعني 1, therm يعني temperature. So isotherm يعني constant temperature. We notice on the phase diagram there is a eutectic isotherm below which everything is solid. So this is the line which is called the eutectic isotherm. That's an isotherm, that's a constant temperature, but it is also related to the eutectic because it happens at the eutectic point. This is what we mean by that. Clear?
Clear.
Any other question?
دكتور في
Yes.
eutectic equation كتبنا إن 8% و 1.9 91 كتبناها لل AG. كيف نعرف إن هي لل AG أو لل CU؟
8% from the صح? Of course, when I don't want you to memorize this equation here, I want you to be able, if I give you the phase diagram, to be able to, I ask you, for example, where is the eutectic point? You should know that it is here, صح? Then, now, I don't want you to memorize this. Listen, I don't want you to أضرب عصفورين بحجر. I don't want you to memorize this. I want you to understand it. How do we get it? So when you come down from there, this is where you can express how the eutectic transformation happens. That's the second thing. The third thing, how do you write it? Yes, being just above that point, you know how it is that the composition is 71.9. صح ولا لا? Because you just drop there and you read it, but the number is written there. Now, as we come down, just below the eutectic ice, how do we get the composition? We have two phases, alpha and beta, alpha and beta. What is the composition of alpha and what is the composition of beta? We drew a toy line, and the same thing which we have done in the previous phase diagram. We draw a toy line. It's going to intersect with the alpha honey, so you get the composition of the alpha. And it intersects with the beta phase here, you get the composition of the beta. The high composition there, it's the composition of the beta. And this composition is the composition of the alpha. This is how we are getting it. Did I answer your question?
لا دكتور.
لا.
الحين كتبنا دكتور إن 8% by weight AG.
Yes.
على الرسمة مو مكتوبنا لل AG.
شنو؟
مو مكتوبنا لل AG.
وين مو مكتوب حق ال AG؟
الحين مكتوب بس 8.
شنو؟ هو مكتوب 8 تبينا
يعني.
هو يكتب لك يعني 8 for AG يعني؟
لا يمكن يكون للسيو. لا كيف نعرف انه للايجي او السيو؟
نعم كيف
نعرف انه للايجي او للسيو اذا بس مكتوب 8 يعني؟
هو أكلا عندك ال values which are given in this one are for the AG. أكا composition weight percentage AG. صح? So therefore when we are talking about the numbers which are given here will be for this axis which is shown for this the values of the composition of the AG. فإذا عندي رقم هني موجود أنا قال أقول لك and this is 8% by weight AG. That number هذه طبعا ممكن نشيل هاي الأرقام. We can remove them like that. We just erase them. And you draw the tie line and then you intersect there and you come down here and read the number here بالمسطرة. When you read the number here, what will be that number? يعني خلينا نقول 10 هني أو 8 هني. What will be this number which you will read? What is it?
8 by weight percent AG.
AG ولا لا؟ الحين احنا 8 اللي معطينك هنا مسهلين عليك الموضوع بس. اوكي؟
اوكي.
كلير؟ عندك in there is nothing wrong with what you're saying because in some phase diagrams both are also shown. يعني and this is why we remove the confusion by saying that what we are reading here is the percentage AG. But here also in some phase diagrams you will see both axes are given. في أرقام هني تنكتب في أرقام من هني. It starts with 100 بعدين نقول 90 بعدين نقول 80 بعدين and that is the composition of the silver. This is done but we've removed the confusion by not writing the other one. Okay?
Okay, doctor.
Any other question please? Okay, if no questions then I'm just reminding you of the lab reports that you have to submit. And also you have a test that you will be having this Thursday, صح؟
دكتور عندي
دكتور اللي عقبها.
اللي عقبها. كنت منتظر تصلحون لي. So it's next Thursday, not this Thursday, which will be at 7 o'clock as Ibrahim, as Khalid Ibrahim has told me, messaged me. So be prepared. And you know which chapters will be, right? In chapter 6, chapter 3, and chapter 4. And also, what else? Yeah, today we're having a lab.
دكتور عندي سؤال بخصوص الريبورت.
إيه بس لحظة واحدة. Today we're having a lab صح؟
إيه دكتور.
يعني نقدر نسوي لاب اليوم صح؟
إيه.
أنا قاعد أخذ معلومات من عندكم. لا إحنا عادة اليوم يمنعوننا إن نسوي شيء عقب الساعة 12 فما في قرار ولا ما في قرار؟
والله دكتور ما أدري. هذا ما سمعنا شيء عنه.
ما بقدر. Okay, keep this. Let me. We need to stop the recording fast because it will take a lot of time.